G'day, John here. Welcome to another PyProx tutorial, helping you understand the impact of uncertainty in data and simulation. In the next few minutes, I'm going to teach you how to use Control Variate Monte Carlo quadrature, otherwise called CVMC for short, to compute statistics quantifying uncertainty in the predictions of a computationally expensive high-fidelity model by using it alongside a cheaper, less accurate model that has no statistics. I will also teach you that, like single-fidelity Monte Carlo estimators that use a single model, Control Variate Monte Carlo estimators are also random variables. I will also teach you that the accuracy of CV estimators on average can be measured by the mean squared error, which can be smaller than the mean squared error of a single-fidelity Monte Carlo estimator for a fixed computational budget. CV estimators can be used to efficiently estimate statistics of a computationally expensive but accurate and trusted high-fidelity model using an ensemble of low-fidelity models. Examples of high-fidelity models include finite element models with high resolved numerical discretizations, for example, time steps and spatial mesh. A low-fidelity model is a less accurate but cheaper approximation of the high-fidelity model. In this tutorial, I'll show you how to use CV estimators with one low-fidelity model. You can find instructions on how to use Control Variate Monte Carlo with more than one low-fidelity model in another tutorial. To estimate a statistic Q, we start with a high-fidelity model F0 that maps, in this case, a 2D random variable to a scalar, and a low-fidelity model that approximates the high-fidelity model. We also need a low-fidelity model F1 from which we can extract its approximation of the desired Q1 exactly. Common examples of such low-fidelity models include polynomial expansions and Gaussian processes. Given two models, CV estimators can be constructed with a simple four-step procedure. 1. Randomly draw samples from the joint density of the random variable z. 2. Evaluate the high-fidelity model at each sample. 3. Evaluate the low-fidelity model at the same subset of samples. And 4. Compute the CV estimator shown at the bottom of the slide. The CV estimator consists of a high-fidelity estimate of the statistic Q0 using the sample Z0 plus a weighted correction, which depends on a low-fidelity estimate of the statistic Q1 computed using the samples Z0 and the exact value of the statistic obtained from the low-fidelity model Q1. Here, A/1 is referred to as a control variate weight. For example, when computing the mean of F0, the CV estimator takes the form now shown on the slide. The CV estimator is designed by construction to be an unbiased estimate of F0. This can be seen by taking the expectation of the estimator, using the linearity of the expectation operator to split the expectation, and noting that the expectation of the known statistic Q1 is just Q1. Consequently, under expectation, the contribution of the low-fidelity components of the control variate estimator cancel. Thus, the mean squared error of a control variate estimator is equal to the variance of the estimator. Being able to derive the variance of a control variate estimator is the key to understanding why Control Variate Monte Carlo can be more efficient than single-fidelity Monte Carlo estimators. Consequently, I'm going to take some time in this tutorial to derive the control variate estimator variance. First, take the variance of the estimator and expand the terms. The resulting expression depends on the control variate weight A/1, so for any sample set Z0, we can minimize the control variate estimator variance by optimizing A/1. To do this, compute the partial derivative of the estimated variance with respect to A/1 and set it equal to 0. Then solve for the resulting equation for A/1. The optimal control variate weight is equal to the inverse of the variance of the low-fidelity estimator multiplied by the covariance of the high and low-fidelity estimators. Substituting the optimal eta into our expression for the estimated variance yields the optimal estimated variance, which is equal to the variance of the high-fidelity estimator minus the inverse of the variance of the low-fidelity estimator multiplied by the covariance of the high and low-fidelity estimators squared. The exact form of the covariance between estimators depends on the statistic being computed. To improve our intuition about these quantities, I will use estimating the mean as a concrete example. The optimal variance of a CV estimate of the mean of F0 is equal to the number of samples n multiplied by the true variance of F0 minus the true covariance of the two models squared divided by the true variance of the high-fidelity model. In this tutorial, I assume that these quantities are known. However, in practice, they must be estimated using a pilot study, and you can learn more about pilot studies in another tutorial. It is very useful to derive the expression on top of the slide, as the tools we will use are needed to derive the properties of many other types of Monte Carlo estimators described in other tutorials. So, all three terms we need to compute can be determined by considering the covariance between two mean estimators Q0 and Q1. The variance of Q0 and Q1 can be obtained by setting Q1 equal to Q0 or vice versa. Now subbing the definitions of Q0 of Z0 and Q1 of Z0. Then take the scalar n outside the sums and repeatedly use the identity shown on the second line to bring the covariance inside the sums. Then use the fact that the sample of Z0 are independent and identically distributed to convert the covariance of each model output pairs into the covariance between the two models, and finally sum up and cancel terms. For a fixed number of samples n, the control variate estimated variance is always smaller than the single fidelity Monte Carlo estimated variance that uses just one model. This can be seen by noting that the term in green is always positive. The plot on the right demonstrates this property numerically. The plot compares the histogram of a single fidelity Monte Carlo estimator, their value specifically in blue, with a histogram of the CV estimated values in orange, computed using a fixed number of samples. The CV estimate is clearly unbiased because the mean of the orange histogram aligns with the true mean depicted by the black vertical line, but better yet, the variance of the CV estimated histogram is substantially smaller than the variance of the Monte Carlo estimated histogram. Thus far, we've ignored the computational cost of evaluating each model. However, in practice, we should use the estimator that has the smallest mean squared error for a given computational budget. In this setting, the relative performance of control variate and Monte Carlo estimators is problem dependent. To see this, first note that the convergence rate of the mean squared error of CV and MC estimators is the same. The mean squared error decreases linearly with n. However, to determine which one is more efficient for a fixed computational budget, we must determine the variance of each estimator for a given amount of computational work. With this goal, let W0 and W1 denote the cost of evaluating F0 and F1 respectively at a single sample Z. For a fixed budget W max, the number of samples that minimize the control variate estimated variance subject to the budget constraint is equal to W max divided by the sum of the costs of each model. We divide by the sum of the costs because for each sample in the set Z, we must evaluate both models. Similarly, the number of samples that minimize the Monte Carlo estimated variance is W max divided by the cost of evaluating only the highest fidelity model. Putting this all together, CV estimators are more accurate for a fixed computational budget when the inequality at the bottom of the slide holds. This inequality depends on the relative cost of each model and the correlations between the models. That brings me to the end of another PyProx tutorial. Hopefully you now understand how to construct control variate estimators and some of their most important properties. Control variate estimators are unbiased, so the mean squared error is equal to their variance. For a fixed number of samples, the variance of control variate estimators is smaller than the variance of the single fidelity Monte Carlo estimator. The relative computational efficiency of control variate Monte Carlo depends on the relative computational cost of the high and lowest fidelity models and their correlation. And lastly, control variate Monte Carlo is only useful when the mean of the low fidelity model is known. See you next time.